to is congruent to a specific set of integers that are relatively prime with respect to the scales of each of the two graphs. In this case, there is no scaling vector for each of the two graphs, despite the fact that u is a function of, y is a function of v, and x is a function of u. So I couldn't find a program that does multiple different variables for the sake of number theory. This is meant more for calculus. Now notice what happens when I make this term factorial. This term y minus 1 factorial. Notice what happens. So it's going to re-render now. Notice what happens. So the whole graph explodes into a multiplicative sum of itself. In this case, I have figured out how to use recursion without actually setting z as an iterative function, which is something you can't do in this program, except for using factorials. Since as the variable number increases, see, it's still rendering, it also has to render each multiple z minus k, each multiple y minus k, y minus 1 minus k for each next rendering. So what happens is, as it renders, the regions that it renders is congruent to the regions that were rendered previously, and this camera being a stopwatch, I could actually notice that it renders certain distinct regions at periodic intervals, and there's a lot of different things you can do with that, including determining the shape and the critical points of congruence along these curves. And all I did was make y minus 1 factorial. So I'm going to revert it back to the original condition, and I'm going to render it again. And wait for it. Oh wait. And this is the original function. Okay. So this was to try to prove geometrically, as a function of variables, that x raised to y minus 1 times y minus 1 factorial is congruent to y minus 1 factorial plus xy, or mod p. Now notice that when two geometric shapes are congruent, not necessarily when numbers are congruent, that they look similar. Now when I try to determine whether they're congruent arithmetically, I ran into this conundrum of whether there would be a disproof of this theory if the numbers weren't continuously continuous, where instead of as a discrete structure, they wouldn't look similar to each other. So I have the final proof here, x raised to y, because I don't have a or n in the computer, x raised to y is congruent to x times 1 plus y. Okay? And that's exactly what I put into the computer. These functions do not have to be exactly alike, and they aren't, but they do have to be similar. This is what x times 1 plus y looks like, the solution to Fermat's little theorem. And this is the ordinate of Fermat's little theorem. And they do approach the same points, and they do take similar shapes. Now here is where simple number theory takes on a new branch of analysis, is that now that I have turned the arbitrary function mod p into an arithmetic translation plus xp or plus px, you can try to see where the two functions are relatively prime or have relative primes, not necessarily relatively prime, and how they are congruent, and where the two functions are relatively equal, not precisely equal. On this arc here, they are relatively equal, but notice this curve is shifted 90 degrees over z. Wait. 90 degrees over z and is upside down compared to the other curve. But otherwise, generally you can see that these two curves are similar.